Okay, so today's the last class. So any questions about last time or course, what we're going to do for the remainder of the class? We could just stop now, right? Uh, okay, so basically we'll talk a little bit about projects at the end of class. Other than that, we'll start today's lecture now. So the goal today is to just go over some topics that I just think you should know about just because they come up so much in MRI. And even if you just have an MRI done on you, it's sort of interesting to see what some of the parameters are. Obviously, there's many topics that we could cover in MRI, and in 9 lectures, we can only really scratch the surface of MRI. Okay. So the first thing we're going to talk about is we're going to revisit sort of this panel here. So this is from a GE MRI system, and we've talked about some of these parameters already. And now we're going to look at this additional parameter here called slice thickness. Okay. So what is that? Well, that's something that the user will set. And essentially, if you think about a volume, right, there's different ways of imaging it. But one of the ways is what's called 2D imaging, where we're going to go slice by slice by slice by slice, right? And so we define what the thickness of the slice is, and then we're going to excite a slice of magnetization, just image that. And then we're going to go to the next slice, image that, okay? And the ordering can be different. We can go like sequentially, or sometimes we'll do all the odd slices and then come back and do all the even slices. There's even new methods now where we can do 3 slices simultaneously, but these are all sort of ways of doing slice selection. So that's in the realm of what we call 2D imaging. And so each slice, we're just going to do the 2D Fourier transform of that. So that's basically using everything we studied in this course. Now, it is possible to do 3D imaging as well, in which case there's not really a slice. You're doing X, Y, Z, and you're doing it 3D Fourier encoding. So that's the other option to do as well. Okay. So we're just going to focus on the 2D imaging, what you would do for slice excitation. So if you remember back to many lectures ago, RF excitation we talked about was sort of the process of taking our magnetization and flipping it away from its equilibrium position. And so by doing a 90-degree pulse, remember we're flipping the magnetization here. Okay. So far, previously we talked about flipping all the magnetization everywhere, right? Now what we want to do, and so that's called non-selective excitation. So that's what it looks like. All the spins are flipped no matter where they are. What we want to talk about today, or just give you a taste of, is selective excitation, because that's used so often. Okay. And so the idea here is um, only the spins in this slice get flipped. Okay. And so therefore, when we're looking at the magnetization of the signal, only those spins are going to contribute. And so we're going to have an image of just that slice. So this is what it looks like in terms of what the longitudinal component looks like. And so you can sort of see here, it starts off at M sub 0. And then after the slice selective excitation, then only the part within the slice goes to 0, right? Because we've totally flipped that magnetization over in that slice. And then before excitation, there's nothing in the transverse plane. And after the excitation, if for a 90-degree pulse, then it goes to 1. Okay, so it's all totally flipped in that case. So that's if you could do it perfectly. And so this is the idea behind RF excitation. Remember, we talked about a little before. We know we needed to excite something, you have to be on resonance. All right. And we also talked about how if you're off resonance, then the magnetization isn't going to get flipped. Okay. So the idea is going to be if I have all these spins here and I want to flip just the ones here, then somehow I have to make only these spins on resonance and everything else has to be off resonance. All right. So that only these spins see the frequencies that help tip them, and these spins up here and down here don't see the right frequency. All right. So that's where we're going to go. So obviously, you might guess that we're going to do this with gradients, okay? Because gradients are what allow us to make spins experience have different law more frequencies. And so here, if I apply gradient here, and here the SS stands for slice selection. Okay, so sometimes this is called the slice select gradient, and also by definition, it's also the GZ gradient. So just sort of one of the conventions is in 2D imaging, the Z gradient always the slices are always along stacked along Z. Okay. So here's the idea. If I apply a gradient, then the frequency of the spins varies, right? These spins have a higher frequency than these spins. And if I only want to excite spins in this slice here, then whatever excitation pulse I have should just have frequencies in this frequency band. Okay. And then because then that's only going to excite these spins and it's not going to excite these spins that are at different frequencies. So that's the basic idea. So this leads to this concept of slice selection. So it's saying in this delta Z slice, if I have a gradient, there's going to be a spread of frequencies, F. Okay. And in the ideal case, if I have a rectangular delta Z, I'm going to have a rectangular delta F. And so I can represent that as rect F over some bandwidth. Okay, which is the bandwidth is sort of delta Z times gamma over 2 pi GZ will tell me the frequencies that are spanned by those spins. Right? So if I could apply a pulse that only had this frequency distribution, then I could excite all these spins perfectly. And in fact, we do have one. If I take the Fourier transform of this direct function and I get the sinc function, it means if I play out a pulse that looks like this, a sinc with the right bandwidth, then I will excite the slice I want. Okay. So in fact, if you go and look at MRI pulse sequences, or if you actually hooked up an oscilloscope to MRI systems, you would be seeing sync pulses like everywhere. Okay, because this is used so often. All right. So it's sort of interesting because when you first learn about syncs, it's like some mathematical concept, but in MRI, it's used like all the time. All right. So this is sort of a nice example, a physical example, because obviously thinking about spins and stuff is not what you experience in your everyday life. So this is what's called Barton's pendulum, which I didn't know about until about 10 years ago. All right. So here's the scenario. So they basically have this string and they've got these different pendulums of different lengths, right? And if you go back to, your physics class, you know that the period is going to be like square root of L over G or something, right? So you'd expect the longer ones to swing more slowly and the shorter ones to have a faster frequency. And then this will sort of have an intermediate frequency. So this is like a gradient, right? Because these pendulums are going to swing at different frequencies. And now here's what we're going to be. This is going to be the analogy to the RF excitation pulse. We're going to start, this is going to swing. It has a certain length, so it's going to swing at a certain frequency, right? Okay. So that's going to be like my RF pulse. And so what you're going to do is you're going to look at this movie and you're going to sort of see, you want to keep an eye on when this starts moving, which of these starts swinging. Okay. So hopefully this plays. So at some point you'll see a hand come in and grab the pendulum. Let's see where that is. So right now it's just randomly moving around. Oh, there's the hand. Okay, so here's the RF pulse. Okay. So you notice they all start swinging a little bit, but after time, only this one is really excited. See that? Okay, so that's basically slice selection. Okay, essentially, you give the spins in a certain band in a certain location have a certain frequency. Your job is to deliver that frequency, so only those spins get excited. All the other spins don't get excited. So Barton's pendulum. You can watch the whole YouTube video online. So we're going to walk through this together. So for example, a typical case, what it might be, the user might say, I want a 10 millimeter slice, and you're given an RF pulse, some sync, and that sync looks like this, right? And has the first zero at T. So, and that T in this case is say 400 microseconds. And then you have to figure out, what slice selection gradient do I use? So typically that means this is the RF pulse. And then while I'm playing it out, I have some GZ gradient on. Okay. So I need to know the amplitude of that and also what's the amplitude of that. All right. So it turns out that you can use all the concepts we've developed so far to solve this problem. So for example, we know that we just said that the bandwidth, the frequency spanned given a gradient GZ and some width delta Z is going to give me some bandwidth. Okay. And we also know that the bandwidth of this pulse, since from Fourier transforms, is just going to be this T, the bandwidth is just going to be 1 over this T. So if this has its first zero at T, this has a bandwidth of BW, which is just 1 over T. And so therefore, we can set up an equation like this, and we can solve for GZ. So the idea is just by knowing the sort of Fourier transform pairs, that's sort of the underlying theory behind a lot of what's going on in the MRI pulse sequence. And similarly, you could figure out the size of A by because you know the area under a sink, right? We've already done that before. And so you can figure out what you need to get that area correct. Okay. But I'm not, since it's the last day of class, I'm not going to expect you to go through that math. So we're just going to focus on high level concepts today. So typically what you're going to see is you're going to see an RF pulse, a sync pulse, some gradient that's selected to select the slice. And there's typically going to be a slice refocusing gradient because at the end of this slice, the spins are out of phase. And so you do need to refocus them. Okay. And then here is our typical spin warp pulse sequence. And so now we sort of have the building blocks of an entire pulse sequence. Okay, so you have the RF, the slice select, and the read and the phase encode gradients. And then basically at the ADC now is what's measuring your data. So basically, if this was a rectangular object, then you would get a sync as your Fourier transform, and the spins hopefully would all be in phase at kx equals 0 for a gradient echo.
Okay. Question.
Yeah.
Can you explain again what the slice refocusing gradient is, please?
Yeah, I can't really go into detail, but here's the basic concept. So this RF pulse, even though it's this really complicated sync function, it clearly has a big peak, right? So you can think of it does most of its action here. Okay. So you can imagine I tip most of my spins at the middle. And now it's just a gradient. Those spins are going to be dephased by this gradient. And so I need to undo that dephasing with a negative gradient, such that at the end of here, the gradient area is 0. Okay, so it's essentially like what we did with gradients before. At this point, we assume everything is in phase, right? I've applied gradient, it's going to get things out of phase, but I can undo that with a gradient of equal and opposite area. So it turns out the exact answer you actually have to do by simulating, and it's not quite equal the area. It's like 6% greater than the area, and it depends on the details, but that's for another course. Okay. Okay. So, and then this is just saying that all this stuff can be understood as a K-space excitation. So we can design these pulses. So we already sort of saw that. We said, oh, if I want a rect function in space, I need a sync function for my RF waveform. So that's one Fourier transform pair. It turns out you can extend this to multiple dimensions. I'm just going to skip over this now. And you can, for example, say, oh, I want a circle. And then you can define what waveform you want by just take the Fourier transform of the circle. You can get it even more complicated. In this case, the investigator took a picture, I believe, of his wife. Okay. He digitized it, took the Fourier transform of that, and used that Fourier transform to program the RF pulses. And essentially, then this is the MR this is the MR image of his wife. And essentially, what he did was he programmed it so that the spins all lined up to impose the image of his wife in the spins, and then he imaged it. Okay, so that's either really cool or freaky, but it just shows you what you can do. Like this is sort of more like this is what's possible if you just have this view that any pattern. It turns out that any pattern you want in your object, you can implement it by taking the Fourier transform of it and putting that into your RF pulses. So it's sort of like the reverse, right? Previously, if we want to image an object, we had to apply the gradients and then read out its Fourier transform and then transform that. Now we're saying if I want to actually impose an object, I just need to know the Fourier transform of my object and use the RF and the gradients to impose that into my object. All right. So one of the places this is useful is cardiac tagging. So there might be one project on that. So here is the idea of I'm going to impose a bunch of stripes, right? So you can imagine if I just had a sort of a number of impulses, right? That's going to give me impulses in one domain, gives me impulses in another domain, right? So I can imagine imposing impulses in my object, right? Just with the RF. And then the nice thing is, it's not like I'm just drawing these lines on after the fact. These lines of magnetization are actually in the object itself, right? So then when the object deforms, like the heart, those spins follow the object. And so therefore, when I image this, I can start looking at things like stress and strain. All right. So I think there might be one project on that. Okay, so that's all I'm going to talk about for RF. So the most important thing is just to have a vague sense of sort of, the slice selection, and then just know that the slice selection is just the simplest case of this sort of excitation case space, and that you can sort of go further and you can sort of essentially design any pattern of magnetization you want and excite it using the right combination of RF and gradients. Okay. Okay, so any questions on that? All right. So the next topic I want to get to is I want to talk about noise and how that relates to some of the other parameters that technicians set on the console. So I think you saw this in a previous lecture that Professor McVeigh gave, which is clearly, when you acquire an image, you do have to worry about, how much of it is signal and how much of it's noise. And typically, there's always going to be a trade-off, right? If you have something with no noise, it's going to take you forever. And if you do it too quickly, you might have too much noise. And so uh, in practice, the clinician has to decide on what's the right trade-off. So we'll talk a little bit about some of the trade-offs they might make. Now, there's also a trade-off that I think you've seen before in terms of there is this trade-off where there's more noise. And because if the noise is random, you can sort of reduce it by averaging, right? By blurring it out. And so it is possible to sort of reduce the noise, but the problem is you're also reducing your resolution, right? You're smoothing things out. Okay. So that's also not necessarily a great solution, although sometimes it's the best you can do. Okay. So let me just walk through this slide to give you the sense of what we're talking about. So no matter whether you're doing MRI or any field of science, signal noise ratio is always basically just like the signal amplitude over the standard deviation of the noise. Okay, so essentially even things like a T statistic or anything you do are essentially everything always comes down to what do you care about and what's the noise. Okay, and so all of statistics is basically that, you know, at least the first order. Okay. So it turns out that in MRI, but also pretty much any modality, SNR is going to be proportional to measurement time, the square root of that, times the voxel volume, times sort of other things that control the value of the signal, such as, so here we've written as some function of proton density T1 and T2. So we've already seen that, for example, you can adjust the signal levels depending on the pulse sequence, right? And what those T1s and T2s are. So then the question is, what is the measurement time in MR? Okay. Well, first of all, it's the time to collect all these points in case space, right? That's essentially the measurement time. So remember, every delta t, right, we collect one of these dots, okay? So then we have n read of those dots this way and n phase of those dots that way. So this is the total time to acquire that amount of case space. All right, so that's one sort of thing. And then the other thing is what we'll talk about is next, which means that, I might decide going through case space once isn't enough. So maybe I need to go through it many times and average it. And so that's one of the things we're going to look at, right? So actually the two things we're going to look at are the effect of next and also the effect of this delta t, okay? Because as you can see, once I've set my matrix size, like the number of recent phase encodes, then that number is set. And then, but if I change delta t, if I make delta t bigger, that's going to increase my measurement time. So to expect that to increase SNR. If I make delta t smaller, that's going to decrease SNR. So we're going to look at the trade-offs of that. And these are just the resolution elements. So this, for example, would be the slice thickness, right? For 2D acquisition. And then the delta X and delta Y are just your voxel size. All right. So there's all these things you can trade off. So we're just gonna look at a few of these trade-offs just so you get a sense of what people do in practice. Okay, so the first thing we're going to do is just identify where this is on this thing. So first of all, the two things we're going to look at is next. Here it's set to 1. So next is sort of like the number of excitations, essentially how much do you average in K-space. Okay, that's one of the things we're going to look at. The other thing we're going to look at is bandwidth. Okay, and this is going to be basically 1 over delta t. All right, so we're going to look at, so these are two things that are typically adjustable by the user. And so we're going to look at some cases of, why you might choose one setting over another setting. Okay, so just to remind you, bandwidth is different manufacturers have different definitions. For example, GE defines bandwidth as 1 over delta t. So here, say the example bandwidth is set at 125 kilohertz. Siemens defines it as bandwidth per pixel or hertz per pixel. So it should be so this should be bandwidth, let's see, hertz per pixel. So this is just essentially, uh, instead of 1 over delta t, it's 1 over the entire length of this readout gradient. Okay. So it's n read times delta t, which is equal to 1 over this tau sub x. All right. So for example, you sort of see here, this bandwidth here is in this units of hertz per pixel. Okay. And so here's the idea of bandwidth. So for example, a high bandwidth pulse means that delta t is going to be small. So we're going to go through K-space very quickly. Okay. A low bandwidth pulse means we're going to take our time. Okay. In each of these cases, this is for the example, the Fourier transform of the rect function. And in a medium bandwidth case, then that's sort of immediate, intermediate amount of time. So because we're taking more time, we expect the low bandwidth to have higher SNR than the high bandwidth. So the question is, why would you ever use high bandwidth, right? Why not always use low bandwidth? Because don't you always want to increase SNR, right? The answer is yeah, sort of, okay. But with all things in life, there are trade-offs, okay? There's always, you get something, but you lose something, all right? So this is, so definitely it does help with SNR. So for example, here, the bandwidth is 30 and it goes up to 600. And you can sort of see the SNR goes from a relative value of 200% to 50%. So we've given up a factor of 4 in SNR here, right? And if you look at these images, that's a pretty good looking image. And you get over to here and you can sort of start to see some of the graininess here in that image, right? Right. I mean, it's still usable, but it's just, it's not as high SNR as the other one. So here's sort of the trade-off. With lower bandwidth, you do get higher SNR, but then you're going to get some of these other issues. And we're going to look at some of these issues. Okay. And then for higher bandwidth, you get lower SNR, but you also sort of deal with some of these issues. So there's this trade-off here. Okay. So let's take a look at some of that. So here's one of the trade-offs here is that, here you high SNR, low SNR, but because the high SNR allows you to go faster, because the delta T, you're spending less time acquiring K-space, the total time of this acquisition was 3.5 minutes, and this was 2 minutes. Okay, so this is high bandwidth. Sorry, this is high bandwidth and low. Okay. So it may turn out that in some cases, if you want to go faster, you're saying, well, I just need to go this fast. And so I'm just going to accept whatever SNR I can get. Okay. And so one of the ways you can do that is by increasing your bandwidth. All right. Another case is, remember with low bandwidth, it takes longer to go through K-space. So there's more time for the spins to just do whatever they want, right? So for example, we saw in fMRI, the longer you wait for the spins, they can have more time to dephase, okay? So essentially, anything that's not ideal will make the spins get out of phase and sort of mess up your sort of ideal imaging. And so what that happens is, for example, with metal artifacts, it tends to lead to a lot of blurring and smearing at low bandwidth. And then at high bandwidth, you sort of can deal with some of that. Okay. There's still some artifacts here, but it's much better than here. Right. So there are cases where, yeah, I mean, it's got lower SNR, but it dealt with the artifacts. Okay. This is just sort of, okay, so then now we're going to get into, so that's bandwidth. Now we're going to get into nex, okay? So this is number of excitations, and as you'd expect, the SNR should go as square root of nex, okay? And this is essentially this what you see in all of science, right? Basically, the more you average, then the signal looks better. And but it's a costly process because it's basically square root of time, right? To double your SNR, you have to spend 4 times as much time, right? So that's why you're always sort of looking at are there other ways of reducing the noise as opposed to averaging. But the basic idea is fairly simple. You essentially, instead of just getting one K-space acquisition, you get two, and then you average them together. And so essentially you're reducing the amount of noise you have in K-space. Okay. And so here's an example here where, for example, let's look at this example here. So we start off this example where it's a highest NR in the field of view is 200. Okay. And then what they did was they reduced the SNR to 100. Okay. So they have the FOV, or sorry, they have the FOV from 200 to 100. So that means that each of these guys goes down by a factor of a half. Okay. So the SNR would be reduced by a factor of 4, right? Because I'm reducing the voxel size, right? And so then to get that, they increased their nex to 4. Okay. Now in this case, that should only get you a factor of 2. So maybe they'll only reduce FOV in one direction, although they did it in two. So I guess what I would say is these slides I got from this website, mrimaster.com. When I go through the numbers, I actually don't find their numbers to be correct. So use with caution. The overall idea is correct, but the exact numbers aren't correct. So in fact, this case, I think they're off by a factor of 2. Okay. Um, but the idea is correct, is essentially because I took a hit in SNR by making the voxel smaller, so each voxel now has less spins in it, so there's less signal. I've got to increase the number of averages to buy back some of that SNR. So that's one of the trade-offs you might make. All right. Here's another trade-off that you might make, which is in this case, they kept the FOV the same, but the matrix size went from 256 to 256 to 320 by 320. Okay. So each of these, the resolution went down by a factor of 256 over 320. Okay. And so if you multiply those together, you get 0.64. They say it's 72%. So I don't really know how they got that number either, but it's in the right direction. It's the right idea that because these voxels are smaller, it is a little noisier if you can sort of see that versus this, right? It's subtle, but it is noisier. And so then in this case, they get back that they can get back the SNR by going to a nex of 2, but the cost is acquisition time. Okay. It's taken them twice as long to get that. Yes, question.
You reduce the matrix size, how come the acquisition time is increased?
Oh, good question. So why is that? Why do you think? So remember I'm acquiring more lines in K space now, right? So it's going to take longer.
Then I also had lower SNR, so that's why I'm ready.
Oh yeah, that's a good point. So maybe that's where I did my math wrong. So this I should have factored this in too, right? So this would be 320 over 256. Okay, so maybe if we do that, the math will appear correct. So this should be really, I should multiply. Can someone do this math for me? So, so this is multiplied by then, so it should just be 256 over 320. What's that? Anyone? 0.8? 0.72 or 0.8? Okay. Yeah, so we're still not getting the right number. So anyways, we'll have to fix that. Between now and next year, we'll figure out what this is. Yeah, that's a good point. So the part of it is the SNR, by doing the more of these, they did increase the SNR, which I didn't take into account. And then the acquisition time is longer, right? So they are spending more time. Yeah, so that's a good catch. Maybe that solves this too. Yeah, I guess this would also solve this too, because they're probably changing the end read and end phase, but I'm not sure. Okay. Um, and then one last case is here, they increase the bandwidth, right? And so you expect that the bandwidth here is going to go from a high SNR to a low SNR. And so one of the ways you could deal with that is you increase the bandwidth, but then you also increase the number of necks. Okay. So now you have both high SNR, but you also have a fairly sharper image, okay? Because some of those artifacts now are reduced, right? But the cost is time, right? So where you're always sort of in the clinic, there's always this trade-off. So ideally, what you'd like to have all of this and not increase the time. And so that's what a lot of research in MR is about. It's like, how do you actually get better signal, less noise without increasing the time? And as we'll see later, deep learning is a big part of that, right? Because deep learning is like everything up to now is assumed there's random noise and that, we have to just live with it. But if we know that, hey, the signal I want is not noisy, then you can start making assumptions about the signal you want to see, and you can start to get rid of that noise, right? Okay, so that's all we're going to talk about for signal noise ratio, just to get across the idea that there is this trade-off that people make between time and SNR. Okay, and then there's ways of dealing with that, and two of the ways are adjusting your bandwidth or adjusting your number of excitations. Okay, the number of excitations is just a pure sort of, it doesn't change the image quality because you're not changing anything about the timing. So it's just more of a pure, are you willing to spend more time? So it's sort of a no-brainer if you, for example, um, if you're at the scanner and you don't really have much time and you're just like, well, this image just needs to, I just need this image to look a little better, then the simplest thing is just to double the next and just hope that that works, right? But if you have more time to think about it, then you might say, oh, well, maybe I want to change the resolution, change the bandwidth, change the next, and then you get much bigger space of optimization. Okay. Because once you change the bandwidth and other things, and that's also going to affect your image quality, right? Your artifacts will be different. Okay. So this topic now is sort of, we're going to just touch upon, give you a sense of what happens with flow. And so we saw this picture yesterday or on Monday with diffusion, right? So the difference between, and so now we're going to talk about more bulk flow. So with diffusion, it was random motion, right? But with flow, there's sort of some concept that you know what's happening, right? Things are going in a certain direction. They're not just randomly moving around. So in this case, we're going to assume that there's something that's not moving, like the tissue, and then there's something that's moving, like the blood, right? And the idea is if I apply a gradient, this spin that's not moving experiences some lower frequency, so it's going to go counterclockwise. This spin moves into an area of higher gradient, so it's going to go counterclockwise even more. Okay. And then we play the same trick we played with diffusion. We reverse the gradient, wait the same amount of time. This spin here goes back to where it started, right? Because it's spent the same amount of time being slower as it did being faster. So it gets perfectly refocused. This spin here, remember, it got slower, and then as it keeps moving into a stronger part of the gradient, so it speeds up more than it needs to, and it overcompensates. Okay, so it overshoots its original position. And so now we see that this has some net phase, which is proportional to its velocity. All right, so that's the whole idea behind the idea that it turns out that the phase of the spins actually tells you what its velocity is if you use this pulse sequence. Okay. Whoops. What's going on here? Okay, let's see if this works. Technical difficulties here. Oh. Okay. There we go. Okay. Okay, so we're not going to go through this in too much detail, but just remind you that the phase is sort of the integral of the change in frequency, reference to the isocenter, and then that all turns out to be the gradients. What's only different here is before, so this x now, these x, y, and z, before we assumed they were static and not changing. Now we're going to let the X position change with time. All right, so that's the only thing we're going to do. And the simplest thing is just to assume a very uh, simple model where there can be some position, there can be some velocity, and there can be some acceleration. All right. And if we do that, we end up with three terms that the phase depends on this term here, which we've seen before. This is just the integral of your gradient. So this is where you are in K space, right? But then we get this term here that's related to, see, it's got gx times tau, the integral of that. This is the first order moment of the gradient. And this is the second order moment. So we have something that's now the phase depends on velocity times the first order moment of the gradients and acceleration times the second order moment. Okay. First order moment, if you go back to physics, right, you think about if you have a first order moment, it's going to cause things to rotate, right? So for example, if this was a bar and I put a force this way and a force this way, this would have a first order moment. Okay. So that's just written there. And the idea is we have these gradients, just like I just showed you, using that physical analogy. We pick gradients that have typically a zero order moment, zero order moment. So this has no area underneath, no net area underneath it, but it has a first order moment. Okay. And so what happens is then it turns out that if I have this bipolar gradient and I look at the phase, if I have a stationary spin, the phase, remember, it goes one way and then it gets back and is refocused. So it's sort of gets back to where it started. But if I have a moving spin, it goes one way and then it sort of overcompensates the other way, such now that it has a net phase. And that net phase is proportional to velocity. And there's different ways of doing that. Typically, one way to sort of get rid of non-idealities is you might even do this twice. In one case, the phase is proportional to plus the velocity. And then if I flip the gradients, it's proportional to negative the velocity. And then if I take the subtraction of those two phases, it's proportional to 2 times the velocity. And so since I know the gradient strength and I know the timing, if I measure the difference in phase, then I can calculate what the velocity is. Okay. And this is just useful because things are never ideal. And so typically by doing this, you subtract out sort of effects that might affect that are sort of background effects. Okay. So let's just take a look at an example of this. So this is so this method is what's called phase contrast angiography. And you can sort of see here what we're looking at is the color of the image is telling you what the velocity is and also which direction it's going. Okay. So for example, here you see the carotids and the vertebrals, those are the arteries, right? Supplying blood to your brain. And so black means, in this case, it's moving this way. And then you sort of see here, these are your jugular veins. And so the velocity is going in the opposite direction, right? And you see a lot of noise here, right? And that's just because there is noise and things aren't perfectly ideal. It's never perfect, but the main and phase is very noise sensitive. So, but the idea is you're getting a good measurement of the velocity within the vessels. And the other cool thing you can do, now what? Okay. The other cool thing you can do is you can measure this along the cardiac cycle. And so, for example, here we're looking at the left carotid artery, the right carotid artery, left vertebral, and the right vertebral over the initial part of the cardiac cycle. And you can sort of see here, the blood's moving pretty fast in the carotid. It's like 45 centimeters per second, right? So as the heart's, squeezing in systole, it's like whoosh, the blood's getting pushed up, right? And then, so there is quite a lot of variation of velocity over the cardiac cycle. Here's another example where we're looking at the posterior cerebral artery, and you can sort of see here that we're sensitive to flow in this direction. So the other thing is by applying the gradients in different directions, you sensitize yourself to flow in that direction. So if I apply the gradients in this direction, I'm sensitive to flow, and I see that there's blood flowing back from here, the circle Willis, to the back of the brain, which makes sense. And then if I apply the gradient in the right-left direction, then I'm seeing that there's flow going this way, and there's also flow going this way. Okay. and flow going this way and flow going this way. And in this case, there's probably something wrong going here. I don't remember the details of this, but there might be something wrong with their circulation here. Okay, because you wouldn't expect the flow to be going this way on that side of the brain. Right? Another thing you can do is you can apply this, as we said, during the cardiac cycle, right? And so you can gate the acquisition and you can acquire the data at different parts of the cardiac cycle and go back and look at it. And you can also measure an X, Y, and Z. And if you put that all together, you come up with what's called 4D flow, which was invented many years ago, but only now being used because of more good software. And so this is an image that you can generate with 4D flow, showing you can basically track the velocities over the cardiac cycle. All right. Now, one issue you have to deal with is that because we're dealing with phase, remember, once I go past 180, right, I don't really know whether things went this way or they went this way, right? So there is this ambiguity about positive and negative velocity, right? Because I could have to go from here to here, I could have a velocity that was very positive, or I could have equally a strong velocity negative that would get me that way. All right. So that's something where that people have to worry about. And so for example, this is a case here where this is someone's pulmonary artery. And in this case, there's a parameter called VENC. So VENC is sort of the velocity that gets you to 180 degrees. Okay. So that VENC is set too slow. If like the VENC is set at 15 centimeters per second and I have 20 centimeters per second, I will overshoot that, right? Okay. So that's shown here. Basically, if I go from here to here, I'm positive, but the VENC is too small, I will overshoot and it be in the negative region. And that's exactly what's happening here. It looks like in this person, the blood's going two ways in the same vessel, right? Which is plausible, right? I mean, there are cases of very weird flow in people. And in this case, if this was true, you would be worried about this person. This would mean there's a lot of turbulent flow in this person. And the more turbulent flow, the more there's going to be a chance of buildup, of arteriosclerotic scars and things like that. So this would be something that, if it was really true, then you might have to go to surgery. But it turns out it's just an artifact, right? So you don't want to have an artifact and then go into surgery and realize, well, there's nothing there, right? So the idea here is if you see this, then what they do in the clinic is they say, okay, maybe my VENC, this parameter is too small. I'm going to increase it. Okay. So now instead of only needing 15 centimeters per second, they've increased the VENC now to 30 centimeters per second. And when they do that, they see all the blood is going in the same direction. Okay. So this is an example of where there has to be some basic understanding of the underlying physics to make sure that you're not seeing an artifact and interpreting it incorrectly as a physical or a physiological issue. The same thing can happen also within a vessel. For example, especially those of your bioengineers know all about laminar flow, where the blood is fastest in the middle and then slows down at the edges, right? Okay, so that in that case, you need to set the VENC correctly too. Okay. And then the other way we can image flow gets back to sort of thinking about T1 relaxation. Okay. So remember, if I have 2 RF pulses and I have some repetition time, if I wait long enough, then the magnetization can recover, right? But if I make that TR smaller, then the magnetization doesn't typically have time to recover, right? So we can actually use this because it turns out that imagine I have basically some spins here, okay? And as they're flowing in, essentially, and I'm applying my RF pulses here, okay? I apply RF pulses here. Basically, the spins out here don't experience any RF pulse, right? So it's only when they come into this region that we start sort of flipping them down, all right? And as we just saw, the more we flip them, the more RF pulses they see, the lower their amplitude gets. Whereas the ones that are coming in fresh sort of have a high amplitude. Okay, so this is what's known as the inflow effect. And it started off as being sort of considered an artifact. Like people saw this, like, oh, this is not good. We need to fix this. But then someone did realize, oh, actually, this is a really cool way of seeing where blood is. Okay. So happens all the time in MRI where something is considered an artifact either for like a month or a year or 10 years, and then someone else goes, oh, that's a really cool signal. Okay. So as you're doing science in your research, always keep an eye out for what you think is actually a disaster, sometimes turn out to be, the key to your thesis. Okay. So you want to sort of keep an open mind. So this is the concept of magnetic saturation, where we apply repetitive RF pulses. So everything here gets saturated, right? We're sort of knocking it down so that anything that hasn't seen those pulses that's coming in looks really bright. This is another view of that where essentially stuff is saturated and the stuff coming in is not as saturated. And so you're sort of seeing here that inflow effect already. All the bright spots here are spins that have flowed in, okay, and haven't seen as many RF pulses. And so that's showing you where blood is flowing. And then you can get these really beautiful images of the brain, okay? Yes.
Sorry, what does it mean to saturate in terms of this spin or?
Yeah, so it's basically, let's see, it's basically this picture here. So for example, the spins that see all these RF pulses get knocked down to a certain level, okay? And let's say, something coming in that didn't see any of these or only see a few of these wouldn't get as knocked down, okay? Um, And yeah, so let's skip over that one for today. Okay. So what we're going to do is we're going to end with now so any questions on that? So that's just sort of introducing you to the idea that there are ways of measuring flow, and two of the most common ones are using phase or this time of flight. Okay. Is there a question? No. Okay. All right. So we're going to end with a little bit of sort of discussion that I think we touched upon a little bit at the beginning, but now that you have a better sense of what goes in an MRI system, hopefully this will make a little more sense. That MRI traditionally has been super expensive, right? It's $1 million per Tesla, right? So if you want to buy a 3 Tesla system, it's about $3 million. Okay. Not only is it expensive to buy the machine, but it's expensive to site the machine, right? Like right now, like we're looking at some renovation costs, it might be like $1 million or more to site the system because you've got to have the structure to support the magnet, you've got to have shielding, you've got to have a place for the helium to vent in case there's an accident. You have to have the power there. You've got to have the cooling. There's a lot that goes into having an MRI system working, right? Sometimes the magnet is actually the cheaper part of it. For example, if you're trying to put a magnet in a city hospital and you got to go into the basement, it can be very difficult. Okay. And then what's even harder sometimes is once you've got the magnet in there and you want to upgrade it 10 years later, that's really expensive now because you got to, get that thing out. All right. So the main cost of the magnet has traditionally been the magnet itself. Okay. And then the gradient amplifiers and the gradient coils are next. And then it goes to the RF amp. The tables and covers, I'm surprised they're that expensive, but I guess so. The RF coils and the computers and the small signal electronics. So it's really the big power stuff that takes up the cost. And so by reducing these things, then the idea is, can we reduce the cost and make MRI more accessible? Okay, because it is not very accessible. Okay, this is from Siemens, so they don't list the US here. But you can sort of see here when this was done, it was, the number of MRI systems in Germany is much more per person, per million inhabitants is much more than Canada, and then Ghana and India are listed there. And I think this is about 4 years old. Okay, so the prevalence of MRI is quite unequally distributed. In the US, we have a lot, so we think it's normal. But if you go to a lot of other countries, it can be very difficult to get an MRI.
Question.
Yes.
Is the electricity bill something like important in the price as well, or?
Uh, the magnet itself doesn't take electricity, so it's more running the gradient amplifiers that takes the electricity. I don't, I, I don't know what our bill is because at UCSD we don't pay that. We just pay a fee for the building, so it's not. I don't actually know how much that bill is, but it's a lot. I mean, those are like 1 megawatt amplifiers. So yeah,
Is the magnet permanent? Or is it out?
we'll get into that. So typically the magnets you see clinically are not permanent. They're basically remember they have the superconducting wire, right? And then there's liquid helium that surrounds it. And so once you charge it up, um, it is that current keeps going, but it's not permanent in the sense that if you get rid of the liquid helium and things heat up, then that magnetization will go away. But we'll talk about some permanent magnet solutions that people are looking at. Okay. So yeah, so getting to that, one of the things that people are trying to do to reduce the cost that we touched on previously is making it so that you don't need so much liquid helium. Okay. And so there are better sort of what are called conduction cooled magnets now that don't require as much helium. And so, for example, this one here is actually turning out to be a very successful magnet, 0.55 Tesla, free max, 80 centimeter bore from Siemens. Just really easy to site and does a pretty good job for most cases. Okay. Um, the other area that people are going into is then smaller or more portable magnets. Okay. So there's sort of two things to think about here. One is the idea that there are certain use cases, for example, imaging neonates, where imaging, having a big magnet isn't really necessary. So you can think of scaling, and once you scale things down, then you don't need as much liquid helium, you don't need so much power. So there are sort of cases where you might want to just, for example, in this case, they've got these little tiny little magnets for neonates. Okay. And so the idea is you want to be able to have these smaller footprint, and it also makes it so that, for example, you could then situate this in the NICU, right? You could put it where the point of care is, as opposed to having to take the baby all the way down to the MRI suite, which might be many floors away. Okay. So there is this idea that um, you can reduce costs and also have a better experience by sort of having special case magnets. And the other one that I think we talked about before is this one here, Hyperfine, which is probably the most well-known portable magnet now. This is the one where we could wheel one in here, plug it in, and we could be scanning in 5 minutes. Okay, so that's pretty cool. Right. And so this is the one that's at 0.064 Tesla, so very low field strength. And essentially, it sort of tries to apply a lot of the concepts that we've talked about. So for example, it does the initial processing in case space, right? It does advanced gridding. Advanced gridding is just saying because it's such a low field and it's got to acquire things relatively quickly, it doesn't necessarily acquire all of K-space line by line by line. And it might use what are called non-Cartesian trajectories. And so the gridding is getting you from something that's not Cartesian, that's not uniformly sampled, to something that is uniformly sampled. And then they do a lot of advanced processing. Examples for, I think there's a lot of deep learning here. And so this is, for example, that advanced gridding. So for example, this is what the K-space data that they bring in. Okay. Here you're seeing that, that adjoint matrix, remember that we saw, the encoding matrix, the Hermitian impose, the Hermitian transpose of that. And so that's the initial image they get. And then they apply additional deep learning to get this image here. Okay. So this is an example of deep learning where they do an initial estimate using Fourier-based methods, and then they go off and try to get a better image later. Okay. And so this is a paper that just came out in August. So there is now a study going on to look at diffusion-weighted imaging and seeing, could you use this in the clinic for looking at stroke patients? Okay. So now that you know a little bit about diffusion, you can sort of see here these areas of high signal intensity, right? Where now you know that the diffusion in this area is less, right? There's been tissue damage here, so therefore diffusivity has gone down and the MRI signal is higher, right? And so with their previous generation, you couldn't really see that, okay, of their hardware and software. And so they've been working over the last 3 or 4 years to make it so that now they're actually getting a sense of it, okay? And so, for example, they said that they made Earlier hardware and software generations were unable to reliably detect DWI lesions. Okay, so that's diffusion-weighted imaging. However, modifications to gradient coil and amplifier design, so somehow they did something with the gradient coils, to the latest generation device and deep learning algorithms optimized for DWI and flare. Flare is these images over here, okay, where they've basically tried to null out the liquid using an inversion pulse. And so you can sort of see here, even a few years ago, they were doing pretty well with these flare images, but now they're doing even better. And so the idea is by they sort of know what they're looking for, right? And that's the whole idea of deep learning. If you sort of know what you're looking for, then you can optimize your recon to do a better job. Okay. And then getting to your question about permanent magnets. So, and I don't remember what the hyperfine did. I'm not sure anyone's doing it. I used to know what the hyperfine magnet was. I'm not sure what it is now, but that's you can look that up. But there are other groups that are doing even more sort of like next generation. So for example, here, you can sort of see here, they're making the magnet itself in this like bulb shape, right? Out of little permanent magnets. Okay. This is what they call a Hallback bulb. And so this is something that they're proposing for emergency department or intensive care use. And essentially you can sort of see here, it's sort of they're flipping the design now, right? It used to be we've talked about the magnets here, the gradient coils are here, and the ARF coils are here. Now you see they put the gradient coils on the outside, piezo magnet in the middle, and the RF coil inside that. So once you can start going away from these traditional designs, there can be a lot of creativity in determining, what the best uh, architecture is. And then here is sort of something that's even more sort of out there, which is here they're using the Hallback magnet to sort of make like a hair salon kind of magnet. So the idea is you could just go in and get your brain scanned. Okay. So I think there is you are going to see a lot more of this desire, especially with improvements in deep learning and hardware and software getting cheaper. That what can we do with lower cost magnets? Okay. So I think there's always going to be a space for very high end magnets where people are trying to push the boundaries on what you can see. But in terms of public health, I think there's also a desire to how can we get this technology out to more people? And you don't necessarily need, it's like not everyone needs like the fastest sports car in the world, right? You can get most people are fine with sort of, a car that just runs. Okay. And so that's the trade-off is like where do all these things lie? And so I think within that realm, there's a lot of exciting stuff that can be done in MR. Okay, so MRI is about 50 years old, and so I think a lot has been done in the last 50 years, and I imagine there's going to be even more innovations over the coming decades. And so hopefully you've got a sense of at least the basics of how MRI works and some of the challenges and opportunities. So I think we'll end this lecture here. What we'll do is, first of all, are there any like questions about that like you've always wondered, well, how does something work? Okay. Yes.
Not towards that, but towards a different point. So you've been talking about GE, Siemens, and
Yeah.
Philips,
Yeah.
is there is it that's because the only game you've heard is that is the ones dominating the market, or are there also like new players that have other solutions, or how come it's on the big market?
Yeah, that's a great question. I think so there's a number of answers. One is I would say there's more competition now than there's ever been in terms of early on, and there have also been companies that used to be part of it. Like there was a company called Picker that went out of business. So right now, I think GE and Siemens are the top two. Philips is very strong, especially in Europe and obviously in the Netherlands where it's based. I'm not sure. I mean, it's very it's in Netherlands is probably it'd be hard. You'll be hard pressed to find a machine that's not a Philips, although there are. I do know of some. Um, Canon, which used to be Toshiba, we actually have a Canon system here. Is trying to increase in the market. And then there's if you go to China, there's a lot of sort of companies there. United Imaging is probably the leading company. Um, and the question is, I think they're doing very well in China, but I don't know how much market penetration they have in the United States. Um, it's sort of like when you get into that, it's also getting beyond technical issues. You're talking about ecosystems, right? It's similar to like, if you have an Apple iPhone or an Android, those are the two leaders. And if someone comes up with a better iPhone or phone, it's still hard to break into the market, right? They have to be either much cheaper or much better. And even if they are cheaper and better, I mean, like if you're like Apple is really good at getting you stuck in their whole ecosystem, right? It's like your phone talks to your iPad, talks to my computer. So like for me to switch is hard. And so it's similar in MRI. Like if you're a research group and you've invested all of your technologies into using, say, Siemens or GE, it's very hard for you to switch because it's all that expertise that you have. And every environment is different enough that they make it hard to switch. Okay. Does that answer your question? Okay. Question. Sorry, can you say that? Oh, yeah. Was there? Did this happen or?
Think it was like the professor at Stanford was sending data from their machine to United.
Yeah, I mean it's tricky because a lot of people, what happens is people move from company to company, and I'm not sure if that was the case in here, but for example, a lot of people who started United had worked for GE and Siemens before. But I'm not sure if that's what the issue was. Yeah. Okay, anything else? Yes.
Um, So in case for brain cancer, we have a DPS implant. I know some of the concerns of a brain stimulator is the wire getting heated with it, but they need to do an MRI. But the ones I've seen over at Jacobs, usually the new surgeons will just have an electronic arm instead of doing an MRI.
Yeah, yeah.
But I mean, I've read some literature talking about trying to minimize that or trying to, allow patients with the DBS to be able to get MRI. How do they do that? Like, because I'm thinking you have the generator here, it's a wire, it's a battery. Like, how do they even avoid it getting into having to interfere with all that?
Yeah, I mean, there's a couple of issues. One is remember there's three different coils, right? And so typically, the primary concern obviously is always, whether this thing's going to get ripped out of the body due to the main magnetic field, right? But that you can sort of design things such that there's not enough force. You can calculate the forces on it, and as long as there's not too much force, then and you can use titanium and non-ferromagnetic materials. And so that's where carbon fiber wipers, things that don't, are not going to experience that, you know, uh, magnetic force, right? Then the other issues are, for example, what we've talked about is when the gradients are switching, they can induce DBDT, which then can go on the wires, right? So therefore, you can think of clever designs where you can cancel out the DBDT, for example, So there are ways of trying to get around that. And there's also heating of the wires, okay? And so then on the device design, for example, maybe you go to like carbon fiber wipers or something like that, where maybe there's less heating of the wires. So there's things you can do on the device side. And then on the MRI side, you could say, okay, well, I'm going to limit my gradient strength so that the DBT is limited, right? Or I'm going to limit my RF power. And all these things are limited anyways. And it may just be that for certain applications, there has to be more customization of those. But specific cases, I'm not too familiar with the specifics, but every sort of manufacturer, and if someone's focusing on that those would be the sort of the three main areas that they would have to look at. Okay, anything else? All right, so were there any questions on the homework or the projects? Okay, if not, I don't see anything online, so I'm gonna stop the recording, and then I'll stay around here to answer questions in office hours.